तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody. In our series of lectures on basic electronics, learning by doing, let us move on to the next topic. Before we do that, let us quickly recapitulate what we learned in the previous lecture. We are now discussing about semiconductor p-n junction diodes. We saw in the previous lecture diode as a rectifier, as one of the applications of semiconductor diode. We saw different types of rectifiers: half wave rectifier, full wave rectifier, bridge rectifier, and also we saw shunt capacitance filter, because we do have after rectification some ripple voltage, which is some component of AC voltage along with a large amount of DC voltage. Therefore, in order to remove the ripple, which is the AC component, we used a shunt capacitance and showed how that considerably reduces the AC component in the voltage output. So, now let us continue to discuss about other applications of p-n semiconductor junction diode. I want to talk to you about wave shaping diodes, how diodes can be used for shaping different waveforms. The normal waveform that you have, easy to get, is the sinusoidal wave from the AC mains, for example. Through a transformer, you can get a step down transformer. If you use, you can get a very low 6 volts or 9 volts AC voltage. Now, can I have different waves, wave shapes developed using semiconductor diodes from this sine wave? So, you can see on the screen now you have a positive clipper, where you have an input sine wave connected to a simple circuit which has got one series resistor, one diode in this direction, and one load resistor. So, now if you monitor the voltage across the load resistor, you would find it will have only the negative half of the sine wave. So, it has clipped the positive, therefore, it is called a positive clipper. So, in the original sine wave which is given as the input, you find you have both halves of the, like normal sine wave voltage. But after it passes through a simple diode, we know this already, this circuit, we call this by a different name previously, we called it by half wave rectifier. So, you have only half of the wave. So, this is one kind of a wave shape that you obtain by using a simple diode, okay, which is in this case a simple half wave rectifier. But you know how the circuit works also, I am sure. When the voltage goes positive, the diode is conducting, because this end becomes positive compared to this end, therefore, the diode will be forward biased, and so it offers low resistance, therefore, entire half positive half will go away like this, nothing will come to the load, therefore, during the load it shows 0. But when the negative half comes, this becomes negative, and therefore, the diode becomes open circuit or high resistance, and therefore, the entire load appears across the load, and therefore, the negative voltage comes as shown in the graph. Similarly, for the positive half there will not be anything, and the negative half again you will get output. So, you find one half of the, or the positive half of the sine wave has been clipped, and therefore it is called positive clipper. But you should remember this diode, if it is a silicon diode, it will always drop about 0.7 volts when it is conducting fully, and therefore whatever voltage you get will be less 0.7, or the other way to look at it, when the positive half comes, it is conducting, and then there will be a 0.7 volts across the diode which will be appearing across the RL, and that is why in the actual circuit output waveform that is shown here in a magnified version, you can see there is a 0.7 volts residual voltage which is coming here, and this comes because of the silicon diode. If I use instead of the silicon diode a germanium diode, this will be only 0.1 or 0.2 volts when it is fully conducting. Therefore, it is a positive clipper, but with a residual small voltage of 0.7 still retained on the positive side. So this is one of the very simple applications of using diode to develop different types of waveform. You can immediately imagine what will happen if I invert the diode, if I just change the orientation of the diode. For example, in this circuit, here you find the diode is inverted and you have an input sine wave, the same circuit, everything is identical except the diode has been inverted. So now what is going to happen? It is a negative clipper, because you can immediately guess that the negative half cycles, when this becomes negative, the diode will become conducting, so all the voltages will be shorted by this diode and nothing will appear across the load. But when the positive half cycle comes, this end will become positive, and that means the diode is reverse biased, therefore the positive voltage will appear across the load. Therefore you can see in the waveform the positive halves are coming and the negative half cycles are not coming, and therefore this is a negative clipper. Here again you should remember in a similar case as before that when the diode is conducting, it drops 0.7 volts across it, it is not 0 volts, and therefore you would find there is a residual 0.7 volts at the bottom in the waveform here shown. So both positive and negative clippers are two different types of wave shape circuits. We can also add additional voltages along with the diode to make it a biased clipper, the clipper with an extra bias, right. So for example, I can add another battery over here. I will perhaps show you a demonstration later on. If I have a power supply here in whatever polarity, that power supply will come in series with the diode, and therefore when the diode will be conducting or not conducting will now be decided by the additional voltage source I have here, and that case it will be called biased clipper. You can have two different types, positive biased clipper, negative biased clipper, and things like that. Thereby what I would be doing is I will be shifting the clipped voltage up or down depending upon the extra voltage source I add in the circuit. Okay. Then we will move on to the next wave shaping circuit, which is called a clamper. So this clamper circuit is very useful. What it is also called a DC restoration circuit. Now if I have a normal sine wave, okay, the average DC of this normal sine wave you know is along this, there is equal excursions on both sides of the 0. Therefore when I connect it to a ordinary voltmeter or ammeter, you would find it will read 0 because it is moving DC voltmeter, it will read 0 because it is going up and down all the time at very high frequency, and therefore the average of this will be 0, and that is what the normal voltmeter will show. So you would not be able to see that. But if I now push the whole waveform up so that the 0 line comes over here at the bottom of the sine wave, then it is called positive clamping. You have clamped it so that the entire waveform is only on the positive side. You can also clamp on the negative side, thereby I shift the 0 to the top, tangentially to the top of the sine wave, then the whole waveform is only negative, therefore it will become a negative clamper. So all these are possible just with the same diode and one extra capacitor. You can see the circuit here now. I have the sine wave which is shown here, that is a source, AC source from a transformer or whatever. You have a capacitor connected in series with a diode in the orientation shown here, and there is a load resistor. Now when you look at the output waveform, you will look the output waveform, the average or the DC line has been shifted up, and therefore now you would find the entire waveform is shifted off with reference to 0. So this is called positive clamper. How does the circuit work? Let us try to understand how the circuit is working. Now let us go in slow motion, look at the sine wave. So when you find when the sine wave goes negative, let us assume the instant when the sine wave goes negative. When the sine wave goes negative, that means this end will go negative, and therefore this diode end will also be negative, because the capacitor is a infinite resistance. The same voltage will appear across here, and therefore this will be negative voltage, and therefore the diode will be forward biased, because with reference to 0 or the ground, this will be negative, and therefore this is forward biased. That means this, during this excursion, negative excursion, the diode will conduct, and the entire voltage which is corresponding to the peak voltage of the AC input will come across the capacitor, and the capacitor will get fully charged with a voltage which is equal to Vp, with this plus, with this minus, these two. Now once that happens, you would find when the next positive half cycle comes, when this becomes positive, you would find hereafter for all positive this will be positive, and this will be negative relatively, and therefore the diode will be open circuit. For all other future excursions, you would find the diode will have no more role to play. It has got role only for the first cycle. When the input goes negative, it charges the capacitor to full Vp. Afterwards the diode becomes almost open circuit for the rest of the circuit time. Once it becomes rest of the circuit, it becomes 0, the open circuit or infinite resistance, then you can imagine this whole circuit is now modified as a AC source with a battery. The capacitor can be effectively considered as a DC battery with a voltage equal to Vp, and that now is coming here. Therefore a sine wave in series with a DC source of Vp is coming in series, and therefore you have to add a plus Vp to all the input sine wave that you apply. So at the 0, if you apply plus Vp, the 0 will be shifted by plus Vp. That is what is shown at the output, and every other point will keep on adding that Vp. Therefore the sinusoid will now be riding above a DC volts which is equal to Vp, and that is why the whole 0 is now shifted by this Vp, and therefore you find you are able to get the full sine wave on the positive side only. So this is called, you have clamped the sine wave at the, so that the entire excursion is only in positive direction, and therefore this is a positive clamper. I have shown here the equivalent circuit for the first negative cycle, when this becomes fully charged and this becomes on, and once this happens, then it becomes open circuit here. The diode is considered basically as a switch here, and therefore this now becomes a battery coming in series with the AC, and therefore the output will just become positive clamped. What will happen if I invert the diode? If I invert, before that let me perhaps explain to you. Here again you should remember that this diode is a non-ideal diode, and therefore there will be a 0.7 volts across that, and therefore you would find it will not exactly be 0, but it will be clamped at some 0.7 volts. Therefore Vp minus 0.7 will be the place where it is actually minus, that the 0.7 will be the loss that you would get with reference to the sine input that you have given, and therefore plus 0.7 to Vp, and then to plus Vp, etc. it will go, and therefore you will lose a small information here with reference to 0.7 volts in the positive clamper. That we should remember. Now let us move on to the negative clamper. If I want to have the negative clamper, you can immediately imagine what we should do. I should just invert the diode. That is all I have to do. When I invert the diode, then the whole argument again can be the same, except that this diode conducts only for the positive half cycle, and when that happens, you can see this capacitor will charge with this end positive, with this end negative, and therefore this becomes a supply, DC supply with the polarity changed with reference to the previous case, and once that happens, then the diode is always open, it is never forward biased after that, and therefore I have a AC source with a battery in series with this end plus and with this end minus, and therefore you would find you start with minus when the V input is 0, and then you keep on moving up, and again you would find there is a 0.7 volts which comes over here, and therefore you will be going from minus 0.7 to Vp and things like that. So this 0.7 comes because the diode is a non-ideal diode. If it is a silicon diode, it will have a voltage across it which is equal to about 0.7, and that is what is shown here. So positive clamping circuits and negative clamping circuits are very, very useful in number of applications, especially for example you have a square wave which is moving both positive and negative. You want a square wave which is going from 0 to some 5 volts or 10 volts, then you just put a diode and the capacitor as a positive clamper, then you would find you would restore the DC to the negative end, and therefore it will become a full unidirectional voltage fluctuation or a square wave from 0 to twice the peak value what you will get. And if you use a voltage which is very large compared to 0.7, it will almost be the entire thing will be available on the positive side. Now I will quickly show you a simple demonstration with a simulation. Okay, I have a breadboard in which I have some of the circuits connected. Let me just look at positive clipper. Now you can see the diode is connected in the direction shown with this end positive and this end negative, and now you have a transformer here and you have an oscilloscope here. So I switch on, now the transformer is switched on, I will switch on the oscilloscope. Immediately you can see the positive end has been clipped, and what you get is only the negative excursions of the input sine wave. These are load, this is the series resistor, and this is a diode connected in this direction. The circuit is shown here, the same circuit is implemented here. So RS, which is usually, I have put a resistance here, in general this could be the internal source resistance of any AC input or the transformer as the case may be. So now if I want to look at the negative clipper, let me switch off and take the negative clipper, I will reset. Now negative clipper, immediately you see the direction of the diode has been changed, and the circuit is again shown here, the diode again here also is changed in direction. Now I will switch on the transformer, I will switch on the oscilloscope, immediately you will find the negative half have been clipped and you get only the positive cycle on the oscilloscope. Both the input and the output are shown here. Okay, both of them are very similar, as I already mentioned to you, to a normal rectifier. Now let me quickly switch off and go to the biased clipper. So let us say a biased positive clipper. Now what is happening? You again have the same circuit with one RS and a diode for a normal positive clipper, but in addition you have got a power supply here, DC power supply. So I am using a voltage source, and the input from the voltage source is connected in series with the diode as in the circuit. And now let us see what happens. I switch on here, I switch on here oscilloscope, or maybe I should switch on the power supply, and then I switch on the. Now you can see, because the power supply is having 0 volts, it is equivalent to having no bias, and therefore it is the same positive clipper that you had previously. Now let me try to increase the voltage. I applied 2 volts now. Immediately you can see the waveform has moved up little bit by that 2 volts because it is coming in series. That means I must have here a voltage which is larger than this voltage. If this voltage is V, I must have V plus 0.7 to make this diode to conduct, and that is what is shown here. So this is a 2 volts, that is extra volt that is coming here. Actually it is 2.7 volts it will be, because that 0.7 volts will always come in the circuit. So if now I can increase to 4 volts, 6 volts as the case may be, and thereby I will be able to shift this still further if I want. Okay, this is a biased. You can also have a voltage source in the opposite polarity, and correspondingly it will be shifted in the other direction, opposite direction. So, this is a positive clipper, biased clipper with a positive bias. Now, I will switch off and move on to the negative clipper. So, here again I have a diode inverted, and you can also see the voltage source also has inverted as an example. Now, I switch on the power supply, the transformer and the oscilloscope. You can see initially the power supply is 0, and therefore, it is nothing but the well known negative clipper. Now, if I increase the voltage by about 2 volts, you can see it is depressed by another 2 volts, because it has to increase over and above the 2 volts for this diode to conduct here, and that is the reason why this is coming in this frame. So, the positive clipper and the negative clipper and the positive biased clipper and negative biased clipper can be used for different shaping the different sine wave. You can actually combine them too, that is you can have in parallel one diode connected in the another diode in the opposite direction as a negative clipper, and you can choose the voltages. Thereby you would find you can ultimately convert a sine wave into a square wave if you wish. So, by using 2 clippers in parallel, one positive clipper, the other negative clipper, with a bias also, you can have the amplitude of the square wave to any value you want. So, now I will switch off, and perhaps I will show you a demonstration of the actual experiment, and then we will move on to the next part. Now, you can see on the oscilloscope a positive clipped voltage. You can see this is actually a negative clipper. You can see the negative half is clipped, and you have only the positive half. The corresponding circuit is here. You have the resistor, you have the diode, and you have the load, and the output is coming from a transformer, and the output is measured using an oscilloscope. So, depending upon the direction of the diode, now the diode is in this direction, therefore, you find it is acting as a negative clipper. The negative voltage has been clipped, and you get only the positive half cycle. Now, I can give a bias to this from a voltage source. I will remove here and give the bias. Negative to negative and positive. So, I am connecting a voltage source in series with the power supply. Now, you can see the 0 has shifted. I will show you by just grounding that. Now, you can see this is a ground. So, it is at the center. Now, when I release it, you can see the 0 has been shifted below due to the additional power supply that is coming out here. So, the total voltage will be around 9 volts or so peak voltage, and therefore, this 2 volts is shown here as a small depression here. So, I can again see that this is a most important point. The 0 of the line is here. When I ground the input of the oscilloscope, you see the ground line. When release it, you can see it is moving down. Now, if I switch off the power supply, and then we will restore the positive negative half cycle, you right now get the full wave, which is the input wave. Now, you would find in a moment when this thing is restored, you would find there is a this depression is now is more. When I applied 2 volts, this was shifted up little bit corresponding to the input DC volts. Now, we will move on to the next, which is actually a positive clipper. So, we will, for this, you know what we have to do. We have to interchange the diode, reverse the diode, and you can immediately see when the diode is now reversed here, the rest of the circuit is identical. When the diode is reversed, you would find the 0 just this is about 0.7 volts. So, you can see the 0 is here, and when I release it, it is moving up. Now, if I want to give a bias to this, then I will remove the thing and try to give a bias, then you can see this point can be moved up or down by the voltage applied. Now, can we increase the voltage? If I increase the voltage, you would find, you can see this moving down or up. So, depending upon the input voltage, what is the now, you can see this moving up depending upon the voltage. If you now decrease the voltage, you can see it is moving down. Therefore, you can see the voltage being read there on the power supply, it is about 4.7 volts. Therefore, it is moving up the 0 is still in the same place, it has now moved up by extra voltage because of the extra bias that is provided, and therefore, this is a biased clipper, positive clipper, the positive half has been removed. Okay. Now, let us move on to the clamping circuit, where you know what is going to happen. We will use a diode and a capacitor. We will use a diode and a capacitor, and you would find depending upon the direction of the diode, the capacitor will get charged, and therefore, you would get the additional voltage which is corresponding to the Vp coming across the output load, and therefore, you will see the clamping action. It is important to see how the clamping action takes place. Now, we will switch off the power supply. Now, we have the sine wave, you can see the sine wave. Now, the 0 is here again. Now, if I make a DC, you see in all oscilloscope there is an option here for AC coupling and DC coupling. This one of them you can see AC and DC, the other one is ground. So, when I press the ground switch, you will see only the ground line, that means the input is grounded. I release that. Now, I have a sine wave which is having a 0 at the center, symmetric sine wave, that is because it is AC coupled. Now, if I press this switch, it will become DC coupled. When I say DC coupled, all the voltage whatever that comes in the only the DC part will be coupled, and therefore, you find the whole waveform is shifted. So, this is actually the positive clamping, you can see that the positive end has come to the bottom of the sine wave. I hope you can see that. Maybe I can reduce, you can see now the entire sine wave is with reference to, you can see that above the 0 only, entire sine wave. So, in a clamping circuit, the most important point is how it should be connected to the oscilloscope and how it should be tested. So, if you put AC coupling, I have now introduced AC coupling. If I use AC coupling, because there is a capacitor here, the DC will be stopped, and therefore, you would find the clamping effect is not seen. This circuit, this sine wave is symmetric to the 0. So, you do not see the clamping. Therefore, only when I DC couple, you would find the entire DC comes over here, you will be able to see the clamping action here. So, here what is happening is this capacitor, which is in series with the diode, gets fully charged for the first half cycle when it goes negative, and therefore, that Vp is always coming in series with the rest of the sine wave, and at that time this diode becomes open circuit, and therefore, you have a DC source across the capacitor coming in series with the AC, and therefore, the whole voltage is shifted by that much DC which is corresponding to that Vp. And you can also see there may be a small 0.7 volts associated with this, which cannot be seen here very clearly, but you should always remember that 0.7 is there. Now, if I want to do negative clamping, you know what we have to do? We have to just invert the diode, that is all. When we invert the diode, you would find the negative half cycle will charge the capacitor. Therefore, you will have minus Vp coming in series with the input sine wave, and therefore, it will be clamped with the negative. You can see that the shift has become directly. I have not changed anything on the dial of the oscilloscope, just I inverted the diode. Immediately, you can see the sine wave is now with reference to the 0 line, it is down below. Previously, it was above, now it is below. So, this is negative clamping, right. Now, let us continue. So, we have seen that through an actual demonstration, by using a set of diodes, we are able to have positive clipping, negative clipping, positive and negative clampers, and these can be used for different type of wave shaping. We can also use diodes for multiplication, voltage multiplication. That is, I have given a circuit here, okay. You can see on the screen, this is a transformer. You have a input from the mains 230 volts, and you have got a diode and the capacitor. So it is something like a clamping circuit here, and then you find there is one more diode here connected to another capacitor C2 here, and this is RL. So if you have a circuit of this type, then you can imagine immediately that for the 1/2 cycle, this diode, when this becomes plus and this becomes minus, the diode will conduct, and you will have a positive Vp across the diode, across the capacitor, and that will make this diode conduct, and therefore that will move on to here. During the negative, again this will charge the capacitor through this path. So over that Vp, one more Vp will be building on to this capacitor C2. So therefore you would find quickly that the voltage across the RL, if you take, it will be twice the Vp. So you have double the voltage. This is a voltage doubler. You also call this circuit as a diode pump, because you can see it is taking one charging cycle through this and another charging cycle through this. So it is like two suction and the exhaust pumps of a motion of a pump. So you find the voltage across the RL will be twice Vp. It is a voltage doubler. Now I have also shown on this same screen a circuit that I was explaining to you, how the two clipping circuits can be combined in the same circuit to obtain a square wave from an input sine wave by suitably varying V1 and V2. Now I have shown another picture of the same doubler, voltage doubler, grounded voltage doubler, where I have the two capacitors, and the voltage across this capacitor will be twice the voltage that you apply. So this is a voltage doubler. So in some applications you would find we will be requiring, instead of 220 volts, maybe 440 volts. Then we can use a voltage doubler and obtain that. And here you find there is another configuration for the same voltage doubler, which is called full wave doubler. Here what is that? What is happening? You have got two diodes and you have two capacitors again, but what is going to happen is, during 1/2 cycle, this capacitor will charge from the transformer, this diode D1 and C1 will be working, and therefore this C1 will be charged to plus Vp. During the negative half cycle, you would find this will become plus, and therefore this diode will conduct, this diode will conduct like this. So the voltage will move in the direction shown, and therefore the capacitor C2 will also be charged to Vp. So you will have one Vp here plus another Vp here, both of them are coming in series. It is like two batteries connected in series. Therefore if you measure the voltage across the load, you would find you will have 2 times the Vp, twice Vp. So this is again a full wave voltage doubler. So I have just discussed two different circuits for the voltage doubler. You also have similarly voltage triplers, etc. They can be used for multiplying voltages to large values. Now we will move on to another type of a diode. So far we have seen different types of wave shaping using normal p-n junction diode. Now we move on to a special type of a diode which has got some relation to what we have already discussed. It is going to be useful in applications to whatever that we have seen so far, and that is the Zener diode or the breakdown diode. So the Zener diode or the breakdown diode, the symbol is shown on the circuit. It is like a normal diode with 2 wings shown here in opposite directions. So this is a circuit symbol of a breakdown voltage, a breakdown diode or a Zener diode. Now the characteristic of a Zener diode will be as shown in the figure. So in the forward bias, when the voltage is going positive, this is a voltage axis, this is the current axis. When the voltage is positive, you would find it is almost like a normal diode. It starts conducting from about 0.7 or so, and so you have a behavior similar to a normal p-n junction diode. But when you reverse bias, in a normal p-n junction diode, what will happen? you would find for very large values of voltages in the reverse direction, you would find the diode will not conduct. So, for example, one of the diodes can have even 1000 volts as the reverse breakdown voltage. Therefore, you have to go up to 1000 volts if you really want to go into the breakdown region. That is a normal diode which is used for rectification, because in rectification you maximum have about 220 volts in the mains, or you will usually use along with a step down transformer which will have a peak voltage of only few, maybe 10, 20 volts, etc. And therefore, you will never come into the situation where there is breakdown. But in the case of a Zener diode, we deliberately operate the Zener diode in the breakdown region. So, the application of the Zener diode comes in the breakdown region. Therefore, you would deliberately keep the Zener diode breakdown voltage to be reasonably low, like 4 volts, 5 volts, 10 volts, 24 volts and things like that, depending upon whatever application you have in mind, and therefore, the breakdown voltage will be much smaller for most of the Zener diodes, because their applications are in the area of voltage regulation, about which we will see in some detail later. Right now, let us look at the reverse characteristic of a Zener breakdown diode. You would find beyond some voltage corresponding to VZ on the reverse bias, you would find there is a breakdown, and once the diode breaks down, what is going to happen is the current is going to be very large for very small change in voltage. So, this is the important characteristic of the breakdown. So, once the how does the breakdown happen? Let us briefly explain to you how the breakdown happens. So, for example, let us take the Zener diode with a breakdown voltage of about 4 volts or 5 volts. That means what is going to happen is, when I reverse bias, the voltage will appear across the breakdown or the depletion region of a normal PN junction diode, which I already explained. So, the entire voltage will come across the depletion region. So, in the depletion layer there are electrons and holes due to the minority carriers. Okay. Depletion region in principle has got no charge carriers, but at a given temperature there will always be some bonds broken due to the thermal energy, and therefore, you can have the intrinsic conductivity of very few electrons and holes generated due to the thermal effects. These electrons, they will be now within the depletion region, and the depletion region is a very, very small region of the order of few microns in size, and if I apply about 1 or 2 volts, 2 or 4 volts for example, 4 volts divided by micron will give me a very high electric field in between the depletion region. This high electric field will be able to rip off some of the electrons from the other atoms in the depletion region, and then these electrons will also get accelerated due to the applied field. So, the field, there is a field emission due to very high field, and once the emission happens, they are accelerated by the field, they come in collision with the other electrons in the atom, and therefore, large number of electrons will be generated very quickly, and you will have very large current flowing. That corresponds to the breakdown. It is an avalanche effect. But if you can have Zener diode with different breakdown voltages, those which are below 6 volts are basically due to what is known as the field effect, and they are also called Zener diode, but the breakdown is basically due to field effect, and these are the actual suggestion given by Zener. But there are other diodes more than 6 volts, for example 12 volt Zener, 24 volt Zener. There the voltage is actually, the breakdown happens not because of the electric field, but because of the avalanche effect. So, they are basically avalanche diodes. Those diodes which have breakdown less than 6 volts are called Zener breakdown. The ones which have got more than 6 volts are all basically avalanche breakdown diodes. What is the idea of the avalanche breakdown diode? Avalanche breakdown is there is a large field again, but the depletion width will be very large, and therefore, the field will not be enough to rip off the electrons from the atom, but they are good to accelerate the intrinsic electrons that are there in the depletion region, which will get accelerated, they will hit against other electrons, they will release the electrons, the more electrons are generated, they are accelerated, more kinetic energy produced, still more larger number of electrons are generated. So, quickly you would find there will be a enormous amount of electrons produced due to collisions, and then that will lead to a very large current and correspondingly a breakdown. So, this type of a breakdown, which is initiated by the accelerating electrons, is called an avalanche breakdown. The other breakdown which I explained, which is basically due to the electric field available at the depletion region for voltages which are very small, less than 6 volts for example, are called Zener breakdown voltages. How do we know? There are two different types of breakdown mechanism operating. The best way to know is by using temperature effect. So, I will not go into the detail, but I can just mention to you, if you use temperature as a parameter for a Zener breakdown and avalanche breakdown, they will behave differently. That is what I will tell you. I will perhaps encourage you to look into some books related to this and try to understand how to differentiate using thermal effect the avalanche and Zener breakdown mechanism. Our interest is more on applications, and therefore, let me quickly tell you how this happens. So, when I now take a diode and obtain its characteristics, in the forward bias it will behave exactly like a normal diode, no difference. But when I go on to the reverse bias, you would find if I keep on increasing, you know what is happening in a normal diode. When I reverse bias and keep increasing the voltage, the current will be very, very small because it is reverse bias, the resistance is very high, and the small current is due to the intrinsic carriers, and therefore, the current will be very, very small, of the order of few microamperes. But the moment I reach the breakdown region, you would find there will be a breakdown initiated. Once that happens, the voltage, as you can see on the graph here, the voltage will remain constant, but the current starts increasing on the, you can see the current increases. So, this turning point in current is called the knee point for the breakdown, and there is another upper limit where beyond which you should not go, because once the breakdown happens, you would find the current is not controlled by the Zener diode. The current is controlled by external resistor. That is the reason Zener diodes will always be used along with a series resistor RS. We must include a series resistor RS when we use a Zener diode in applications, because once the breakdown happens, the current will be only limited by the external resistor RS and not by the Zener diode. Zener diode will become almost zero resistance. So, if you do not have a RS, it will be amounting to shorting the power supply, and therefore, you must always have a series resistor in series with the Zener diode when you are operating at reverse breakdown. Now, you can go on with the current in the reverse direction, but beyond some point the current will be so large, there will be enormous heating produced, and that heating may hamper the Zener diode. So, that a Zener diode, instead of breaking down, it may become not usable at all. Because of high temperature, the Zener diode can become defective, and therefore, you should always make sure you limit the current in the Zener diode when it is a reverse bias. So, what is the maximum current that I can have under reverse bias condition? That will be decided by the wattage of or the power rating of the Zener diode. So, you can buy Zener diodes in the market for 300 milliwatt, 600 milliwatt, 1 watt, 10 watt, 100 watt, whatever. So, but what do you mean by that? That will tell you what is the maximum current I can have under reverse bias condition in an breakdown region. And therefore, if for example, I have 600 milliwatt Zener with 6 volts, then you know what is the current that I can maximum apply. I can have 600 milliwatt divided by 6 volts, that is about 100 milliamperes. So, I cannot go beyond 100 milliamperes in a diode which is having 600 milliwatts power rating and 6 volts breakdown voltage when I operate at 6 volts. So, one has therefore the maximum current IZ maximum will be decided by the power rating, and IZ minimum will be decided by the knee voltage, which will be generally about 1 or 2 milliamperes. So, from 1 or 2 milliamperes to about 100 milliamperes for a 600 milliwatt example, you can have any current in between and operate it in the breakdown region. Now, before I go to actual demonstration of the Zener characteristics, I will bring down the most important point with reference to the Zener diode, and that is you find you have the voltage is a constant here, the current is changing. The current is in the y direction, negative y direction, the voltage is here. You would find the voltage is the same for all these currents. They can be this end can be several amperes, this end is in milliamperes. Over a very large range, the voltage is almost constant. This is shown very sharply perpendicular, but in reality it is not. It will have a slight slope. That slope is the resistance of the Zener in the breakdown region, which will be very few ohms, very small value, and that is so the upper limit is decided by the power rating of the Zener. Now we will quickly move on to show you a demonstration of the Zener characteristics, and then perhaps in the next lecture we will discuss about the application of Zener diode in a regulation, power supply regulation. Yeah. So here you have, we will remove the load. Here I have a series resistor and a Zener diode. Is it now forward biased or reverse biased? We have to see. Now let us increase the voltage. You see the voltmeter is connected across the Zener, and there is a current meter connected across at this point in series with the RS. There is a current meter that is connected here. It is showing in milliamperes, and you see first we must do the forward bias. Anyway, it's okay. Now you have the voltmeter shows around 6 volts applied. You get reasonable amount of current, nearly 10 milliamperes of current, and the voltage is only 4.9 volts. You can see here the voltage. Now let us decrease the voltage. As we go to lower and lower voltage, you find it starts slowly decreasing. Let us stop here. Now it is around 2 volts. The current is almost nothing, and it is about 1.5 volts, because this at this stage the current is only due to intrinsic conductivity is not in the breakdown region, and therefore there is no current here. Now let us again increase. As we increase, this voltage keeps increasing. What is the voltage across the Zener is measured by this, and when it comes to 4.9, afterwards the current starts increasing here in the current meter. You can see when I now increase the voltage still further, the current is increasing, but the voltage in the voltmeter still reads only 5 volts. The voltage is not changing, 4.9 to 5 volts. There is only 0.1 volt variation. The variation in the voltage is very small, but the variation in the current is reasonably large. Now forward bias the diode. We will reduce the voltage to 0. Now we will change the diode. So the diode has been changed, that means it is now forward biased, as you can see now. The same meter is there, the voltmeter is there, it is showing some millivolts. Now start increasing very slowly the voltage. You can see it is increasing slowly. We will increase, let us go very slowly, still slowly, starting from 0. Let us go. You will use the fine control, you will use the fine control to increase. You can see, let us wait about slightly more, about 100 or so, still further. Let us increase the voltage. Let us increase the voltage using the fine control. Yeah, now you can see about 200, 300 millivolt. Let us wait there. About 300 millivolt, 200 and odd millivolt. There is no current, and therefore the entire voltage is here across the Zener. Now let us still further increase the voltage. Still further, nearly 500 millivolt. Let us wait now. This around 535 millivolts or so. 0.516 volts is nothing but 516 millivolts, and that is the voltage across the Zener. Still there is a very slight movement in the current, which is not significant. Now let us start increasing the voltage a little more. Now you can see the current starts moving. Now the current is moving, yes, still further, maybe 5 milliamperes. Okay. Now you can see what is the voltage across the diode. The voltage across the diode is only 0.7, which is corresponding to silicon diode. If we still further increase the voltage, right, still to 10 milliamperes. Now what is happening? the voltage across the diode is still about 0.79 only. The voltage across the diode is only 0.79. We have reached around 10 milliamperes. The diode is behaving like a normal forward bias diode. When you forward bias up to 0.6 volts in the voltmeter, you would find there is no increase in the current. Beyond 0.6 volts, the voltage changes very slowly, 0.6, 0.65, 0.7, 0.79, etc. But the current starts increasing on the current meter. Therefore, this is corresponding to a normal forward biasing of a diode, and we saw previously what happens when we reverse biased it. Maybe we will quickly go into the reverse bias once more to highlight that point. Just change the diode. Yeah. Now the diode is reverse biased here, but rest of the circuit is identical. This voltmeter now reads. Let us now start increasing the voltage. As we increase the voltage, you would find initially the diode, there is no voltage drop across the diode. Diode is therefore there is no current here. Please increase the voltage continuously, slowly. Now it is around 4 volts. Applied voltage in the power supply is around 4.6 volts or 4.7. There is a very small current now coming into this, and the voltage here is around not much at all. Now let us go further. Five volts. Yeah. Now you can see the voltmeter reads, the current is around 5 milliamperes, the voltmeter reads around 4.8 volts, 4.81 volts. So this is already very close to the breakdown region, which is around 4.9. So it is 4.8. Only when it comes to 4.8, it starts changing, and the current only now increases. If I increase the voltage, input voltage still further, you see the current immediately increases to 10 milliamperes or so. Now it is about 6.3 volts applied, but 10 milliampere current, but the breakdown voltage remains constant at 4.9 volts. It has not changed. Therefore, in the reverse bias condition, the voltage across the Zener remains constant, but the current keeps on increasing to any value beyond that. If I now keep on increasing the voltage, input voltage, then you would find beyond some range the Zener diode will have enormous currents. Beyond, if it goes beyond the scale, for example, large current will flow through the Zener diode, and the Zener diode will get heated up, and in the process the Zener diode may be spoiled due to the enormous thermal energy produced in this. And therefore, one has to be very careful about the maximum reverse current that can be passed. So your current in the reverse bias condition can never exceed that limit. That limit is achieved or understood by knowing what is the power rating of the Zener. You should know the power rating of the Zener and divide the power rating by the Zener breakdown voltage. That will give you the maximum current that can be passed through the Zener. So with this, if you use the Zener diode, you will be able to use the Zener diode safely. Now we have seen how the basic characteristic of a Zener diode is. You find when you forward biased Zener diode, it acts like a normal diode, but when you reverse bias, it is deliberately, the breakdown voltage is kept very low, so that the breakdown voltage comes within some 10 volts or 5 volts or 6 volts as the case may be, because one of the major applications of the Zener diode is in regulators, voltage regulators. What do you mean by voltage regulator? You want the voltage to be constant, regulated irrespective of changes in the input voltage or changes in the load. Depending upon the load, the current drawn from the power supply will change. So when the load is changing or when the input voltage is changing, still the output power voltage output should remain constant. Then that power supply we call as a well regulated voltage supply. To obtain a well regulated voltage supply, Zener diode can be used as a very useful device. That is what we should look as an application of the Zener diode. And quickly I will summarize whatever we have seen over this 1 hour, and that is with reference to the different wave shaping circuits using simple diode, how you can have positive clipper, negative clipper, and how you can combine them to get different types of wave shapes from sine wave input. Then we also saw about clamping circuit, positive clamper, negative clamper, and they are very useful in several other applications which we will come across in future. And then we talked about a new type of a diode, which is basically a Zener diode, which is used for voltage regulation. And I also explained to you that there are two types of Zener diodes. One is called Zener breakdown mechanism. There are two types. One is the Zener breakdown mechanism, the other is called avalanche breakdown mechanism. The Zener breakdown mechanism usually happens for low voltages up to about 6 volts. If you have Zener diodes less than 6 volts breakdown voltage, they will mostly be operated on Zener breakdown mechanism, which is a field effect breakdown mechanism. The other one is the avalanche breakdown mechanism, which happens for voltages beyond 6 volts, and that is basically due to the electrons getting accelerated, hitting against other electrons, releasing some more, and all of them contributing to a large current quickly through an avalanche effect, and therefore that is an avalanche breakdown. I also mentioned the distinction between the two breakdown mechanisms can be obtained by looking at their temperature behavior. When I heat the junction, what happens to the breakdown voltage? Is it increasing or decreasing? That will indicate to us indirectly whether it is a Zener breakdown or an avalanche breakdown. I also showed you a demonstration of a Zener characteristics, where you would find in the forward bias direction the voltage was increasing around 0.7 or so, the current was increasing enormously beyond 0.7, which is a normal behavior of any PN junction diode. But when I do a reverse characteristics, you would find till about 4 volts or so there was no increase in the current, and beyond about 4.5, 4.6 the current starts increasing. After 4.9, which is the breakdown voltage for the Zener we used, you find the voltage remained almost at 4.9 to 5 volts, but the current started increasing enormously, thereby showing that we are already in the breakdown region. And I also mentioned that especially when you are in the breakdown region, you must be very careful to add a series resistor to protect the Zener diode, because once a breakdown happens, the current is decided only by the external resistor. And then we also should remember that the wattage of the Zener is the most important parameter that tells us what is the maximum current that I can operate the Zener. So in the next lecture we will see the application of the Zener diode in voltage regulating circuits. Thank you.